how discussion on how the basic system works for any operation.
Yeah, like a system consists of ALU and
Mm-hmm.
register files and
Mm-hmm.
then barrel shifters
Mm-hmm.
and
Perfect. So the
catch
thing
memory
is,
and catch
Mhm.
memories.
Mhm. So it is very simple. Like we have seen in a blog section, the ALU will be nothing but our CPU now. That's where our arithmetic and logical unit stuff will be there. The registry, the one you explained, it's technically a memory where it stores the intermittent data or the instructions to process. Um, and the other things are the input output devices that we have seen last time. It could be either keyboard or mouse tracking or any input, double click on an application, then it starts up, things like that. So these three are bare minimum basics for any OS that is functioning with the specifications. Um, so you guys understood the difference between these three, or you want me to go even more specific? The CPU are the one it performs an operation, whatever you're requesting, and memory is the one where it stores the intermittent data. You don't get confused that the data being written on the disk, which is more persistent, you can fetch it anytime. But in the RAM or the intermittent data will be stored for any of the operations. And your input output devices. And whatever the operation you are carrying out in CPU, you need to have a set of libraries to execute that. Um, say for example, I think every one of you guys must have gone through a couple of languages basic training. So sometimes you invoke class from other places or invoke another libraries to your self-written automation script. The reason is the couple of things that you are trying to execute that depends on the existing libraries or it's predefined libraries so that in a way it can work. CPU works in the same. We cannot just to a plain CPU, we cannot just go and ask, hey, give me an exponential of these numbers. So it needs to understand whether do I have an exponential function to perform this task. That exponential function definition that it has behind what we call libraries. And eventually CPU is the one who is going to perform the operations and it's going to use the memory, the RAM uh, in the system to relay the messages, um, so on. You guys understood the difference between the CPU and memory for now?
Yes.
It's
Yeah.
not a rocket science though. It's just simple terms how we see it. The registries are your uh, memories, RAM. With that basic discussion, let's move on to the modules and what is cache that we are going to have. Cache is nothing but the smaller set of memories which are in the same bus that helps us to buffer the loads. In the simplest way, I think the buffer, you guys must have understand back uh, like few years, couple of years back, even the YouTube, whenever we play, it takes some time to buffer and then it plays it around, right? So the buffer section, to avoid those level of buffer section, we use cache. But sometimes based on the network bandwidth, it even overpowers it. But to avoid that particular functionality, we have that cache memory. which is closest to your processor. So the fetch, instructions fetch and data return would be in a seamless way. And it's not the same size as memory. It's smaller size as memory. I'll go in depth on the cache a little bit later. Let's focus on the memory modules. Technically, right now, we have multiple types of memory, but on the module side, we have only two set. We have SRAM, we call static RAM, we have DRAM, the dynamic RAM. Both serves the same purpose. It's not ROM, it's RAM. So uh, whenever there is a power reboot or anything goes on, the data stored on those RAMs is lost. They're using a capacitor in DRAM, dynamic RAM. So whatever the storage that we store, there would be a leakage and it gets refreshed every time, unlike static RAM. All of our servers that we are using, we most likely get the DRAMs. There is no commercial based static RAMs that we have. So that is memory. Now, how does the CPU and memory work together? That we're gonna go further onto it before we move on to NUMA. But until now, does anyone have any questions? If it is getting confused, please do let me know. I'll try to explain it in a different way.
I have a question about cache memory.
Mm-hmm.
What does mean OP cache or OPQ in Gen architecture? I didn't understand.
Sorry, which one?
OP cache or OPQ in a Gen architecture.
Oh, in Zen architecture.
Yeah.
So that part I'll come to it later because that's a good one. I'll just go over the details and then you will know how to relate those specs. Since it's not specific to Zen architecture, I'm gonna go basics onto it, but I'll get back to your question
Uh,
eventually.
Sir, have one question. Now, in MIPS architecture, they generally follow a five-stage pipeline, right? So, in AMD processors, do they follow the same process, or is there in a different approach?
Stages would be the same, but the method of doing those stages would differ. Say,
Okay,
for example, the bus lines could get differ between the memory and the CPU, how we perform the architecture. It's also based on the size of the processor that we are making. I think the Radeon, the one we have, it's 45 nanometer. But yeah, it depends on the size, depends on the use cases. The architecture differential things would change, but the functional stage would remain same all the time.
okay.
Okay, now technically this is how it looks like. How the traditional CPU and memory work together to carry out a process or application or anything like that. Assume you are trying to do the most simplest arithmetic operation, which is addition, 1 plus 2. How it's going to happen? It's exactly shows in here. The IO buses over here uh, that technically connects to the bus to the RAM. So the inputs that you are providing through the system bus, which is your system agent. For every OS distribution, we have a system agent that carries to the RAM. So from RAM, we have two level of caches in traditionally, like in old processors. Why do we have caches over here? From the CPU, get to a RAM, collect big chunks of data, consumes latency. Let me tell you what is latency means. CPU is the one trying to perform the operation. but the data will be initially stored in RAM. That's where the data is stored. So in order for the CPU to fetch those data, process it, and then return the data we call it as latency. The amount of time for the CPU to take a data from RAM and process it and then um, push it back to it is what we call latency. So for CPU to reach this RAM in the same bus directly takes lots of time. That creates a lot of latency that technically lower the performance of the system. So what initially people had done, they had created cache in between, which is technically they created only one cache. And then they've realized that they can include another cache to avoid this issue. So what it does, instead of giving a big chunk of workload, a big thick nodes of stuff, the L1, L2 would fetch in couple of pages over there, and that's what been sent it to CPU. In that way, the processing um, time is reduced a lot. It's like a teamwork. Instead of giving the entire project to one person, if you split all the different aspect of the project and give it to people, then everyone can work parallelly onto it, and then we get a closer deadline to finish the project. That's what they are trying to achieve using the cache memory. Any questions so far now? I know it's a bit tight, but you guys, unless you guys ask any questions, then it will be still locked in your mind.
Is the cache memory common for read and write thing, or is there any cache memory for specific to only a read or a write?
No, it's not like that. But L1 cache alone, if you see on the right picture, there are two sets. We call it L1I, L1D. Initially, that's how they have defined. So L1D is a data cache. L1I, it's instruction cache. The instruction cache contains, assume that example 1 plus 2. The L1I instruction cache will have 1 plus 2, that entire cache along with the arithmetic operation. But once the process has been performed, the value 3 will be in L1D. That's where you get your data cache. So L1 high instruction cache will have both data and operation specific, but L1D will have only the data. It could be input or it could be an output, means result of the operations. But L1D would carry only the data. L1I carries both operation as well as a data spec. But L2, L3, it's common. It's a single bus thing. So it doesn't have a split to store data or operations. So it's common for both.
Yes, got it.
So I have one question.
Mhm.
So now when we write back the data, right, to the RAM, it would definitely store some part of it in the cache. So will it just store it in L1 cache or will it also store in L2, L1 and L2?
So with RAM, it actually technically refreshes. It depends on how well we would like to have that data.
Okay.
Right. So if you just log on with your SSH into some of the node that you are accessing and you're adding an environment variable, it would be only in your TTY spec, which means your SSH session, until you have that SSH session, that environment variable, you can use it anywhere else. But if someone else logs in, or if you log out and then log back in again, you may not have the same spec. So based on where you store, it stores those values in between.
Yeah, but isn't that it would just store in L1, or it will also copy the same data into L2 cache? Uh, do we have a
No,
dual copy for
this is only a processing section. Say, for
Okay.
example, you are adding an environment stating env export a equal to 2 plus 3. You are passing an arithmetic operation. Only specific to that arithmetic operation flows between L1, L2, and the CPU. But the output, once it's stored in RAM, it stays in there based on the validity of your session.
Uh,
It won't go to it won't store it again in L1 and L2 because those operation already done. It
okay,
only needs to store your variable.
okay, okay. Thank you.
Only during the operation we will be using this, but once it is done, again it's cache is another level of RAM. So it just refresh itself. So once L1 knows it transfer the data over here, it just refresh, keep it open so that the L2 can utilize another space over there.
Uh,
Whatever the instruction sending it from L2, so L1 utilize that space.
oh,
But eventually, once the arithmetic operation completed, your data will be in your DRAM.
okay. Because like in few process, we try to use the output of the previous instruction and
Mm.
use it for the next, right? So in that case, how is it going to be? Like, is it going to store it in cache again, or is it directly going to the RAM?
It it comes to the RAM, the output, but like you mentioned, the output of this one you are trying to redirect to the input of another operation. Is
Yeah,
that what
yeah,
you're asking?
yeah, yes, yes.
Then then along with that value, output of first executed command value and the operation you would like to perform and the rest of the value, what you're trying to achieve, it flows both in the same way.
Okay,
It
okay,
won't store. The cache is mostly most let's say cache is more friend buddy of CPU. It's not even for memory. The CPU cannot handle the big chunk one by one. It consumes a lot of time. So instead of that, we are splitting it. We are trying to divide and conquer over here.
okay.
If a processor requests for a input first, it searches in cache memory, like data present is in cache memory or not.
Yes.
If it is not present, it will go to the RAM.
Mm.
So if data is not present in the cache memory, searching the cache memory, it requires a time. So how would uh, how to overcome that thing?
So that part it's a good question. That part we cannot help too much because that is the way the closest memory the CPU could check. If it doesn't have that data, that's fine. It goes to L2. If L2 doesn't have data, it goes to L3 and eventually to DRAM. Uh, because process might not exist at that recent over in here to have. So like I mentioned before, it's a continual big chunk of process if you're trying to run. It splits and it's uh, delegated to each and every section one by one. That's how CPU thinks. So if it couldn't find the next iteration, eventually it has to go to DRAM. That's where the customers right now are reporting a lot of latency. So that to overcome that part here, we have only one CPU. To overcome that part, we are just switching into new modern way, which is NUMA and other configuration, other concepts.
Yes, got it. Thank you.
Yeah, like what is that L0 catch? L0, you have mentioned something, right?
This is not actually an AMD process. I think I took it from Intel one. Sorry. So technically, this instruction that we are having, right? So by means closest to registry, we have another cache. Cache is nothing but not like a big storage like your SD or kind of things. It's anything closest to registers or DRAM. It would be a capacitor. So I believe they have an extra capacitor over here to differentiate these instructions. But this part I'm not sure. I'll get back with you guys soon.
Yeah.
I need to check on the Intel side what they have over there.
Okay, sir.
Any other questions? So technically, how you guys see this one is like getting onto a bus. You will be, boarding at the end of gate at the end of the bus, but getting out at the front side of the bus. So technically, it's one section. You enter only one way and exit only another way. So assume you guys like 50, 60 people trying to get onto a same bus. Uh, think about how much time it would take for all the 60 people to board the same bus and get out at their respective destination. Along with processing the wait time to pick all the 60 people and then drop them in a different location or different processing time. So that's the trade-off that we are working on with this traditional way, because we have only one system bus that flows between IO, RAM, L2, L1, and the registers. That's when we are jumping into concept of NUMA. So any questions until now over here? Uh, Anything specific that we need to focus on? I'll just have a note. I'll catch up in our next meeting. I'll just go over the details specific to that part. Right now, I've noted L0 cache and the Zen architecture questions. Any other things? So, yeah, go ahead. Sorry. If not, let me move on to the next one. So the L3 cache, we call it last level cache. Okay. So in your previous diagram, you must have seen only one core. CPU is nothing but core, we call it. But over here, if you could see, now we have two cores. Say you have two entry, two exit in the same bus. Now, to board all the 60 people, does the time of waiting the bus reduced by half, right? If we have two exit. Logically, two entry point, two exit point. So if we have more than one entry point, technically from half percentage, but it would be less than 100% of wait time that we used to have with one entry and one exit point. So then it came a two socket, it goes on the same level. Other devices use the PCI system agent, goes to DRAM, DRAM control, then fetches back, flows back this way. Now, how do we, so now we realized having number of cores, extended cores, will technically help us to attain more throughput and performance. and less IO wait time, less latency, not less, I would say, latency side, you would minimal latency to reach this part, right? So what the system guys started doing it, these are physical structures. These cores are physical structures. How do we split the physical structure to show multiple virtual structure in such a way? If I split this core into, uh, this is one CPU, one core is one CPU. But what if I split that one physical CPU into two virtual CPUs? So the number of entry and exit points that we're gonna have relatively increases with respect to any system agents that trying to perform an operations, right? Remember the Intel laptop that we used to get, guys, like quad core before i3, i5, i7, even with i7, like there were like a lot of quad core stuff that defines a number of core uh, def, um, exist in the system. So that is the reason we are right now we are not keeping just one core. We are having multiple core. Reason this increases our throughput and performance. Accessing this level of way, but along with changing it physically, if we keep adding more cores, eventually the size of the processor increases. Right now, that the smartphones that we are using, like in a minimal size, if we haven't focused anything on the virtual specific, it would be even bigger phones in our pockets right now. So our approach and the vision started moving towards how do we efficiently use the physical cores. That's where we are getting into a picture of NUMA. What is UMA and NUMA is uniform memory access, non-uniform memory access. Uniform memory access is just one bus accessing that particular core and get back the result. That is uniform. Like assume it's a queue. You have a room and you have one entry, one exit point, and you have only one counter to get through, and you have like multiple people waiting on the queue. Then the queue wait time increases. It can able to process only one people can enter the entryway, and one people get processed, one people would get out. So that's the situation. Most traditional one we had. That's why we didn't have lot amount of speed, even with the bigger um, desktop and other things. Right now, even with the smaller size, we were able to do even faster than we used to do before. The reason, the way the size of the processor has changed and the way that we approach how ALU should perform the operations. I hope you guys don't sleep after this historical view of how CPU and memory would go through.
No.
Yes, go ahead.
Nothing.
Oh, okay. I thought you were saying something. Sorry.
Uh, Sir, I have a question.
Hmm.
Uh, yeah, you said the single core can be divided into two virtual processors, right? So what do you mean by that? Like, how?
So technically, instead of this one, I can tell the system agent, hey, if you're sending it to this side, I have two L2 cache, two
Mhm.
L1D, two L1I. Technically, I'm not a one person, I'm actually a twin. So you can send instruction to uh, either one of us to achieve your performance. But technically, a core can handle more than one thread. which means more than one processing information.
You mean multi-threading?
Yeah, you're right. But instead of just going with multi-threading, it's the way like if there is a person A, and I have two tasks, and then go and tell that person, hey, do two tasks, then he will be adding more to him. You will be a little bit of overwhelmed. So instead of that, I am creating a cloning of himself, or assuming that I instruct that person to carry out one task in his one hand, the other task is in another hand, because he can capable of doing in both hands. But he is only one person. So he will mention to us then whenever the code trying to perform any operation, it checks in the cache, right? So instead of check just one way, it does it in two ways. So the two process would run concurrently to perform the activity.
And sir, I have one more question.
Mm.
Now in the diagram it shows like two cores are attached to one L3 cache. So while accessing the
Mhm.
L3 cache, there might be congestion, right? Like the core one might try to access L3 and core two
Yeah.
also can access.
Mm.
So is there any protocol in which they follow on so that if first core access the L3 cache, then the second core cannot have that access for that point of time? So is there any such process?
I see. Yeah, you're looking for like collision detection or collision awareness kind
Yeah,
of thing.
yeah, because there could be update in the L3 cache, and that
Mm.
update can lose the data for core 2, and again it have to go to the RAM. So there's a loss. It could cause latency, right? So that's the
Mhm.
reason I'm asking this question.
So every system that they are trying to define, I understand what you're asking. They define the throughput and performance of the system before we um, sell it out, because we know how much capacity it can handle from the core all the way in here. But even if this process miss, it next level it checks on the DRAM. So I understand there is a miss. We call two terms over here. What we call cache hit, cache miss.
Miss rate and hit rate, right?
Yeah, that cache hit rate, if it is higher, then performance go until that point. When we started to see a lot of cache miss, then that's the saturation point of our throughput.
Yeah.
So that's the throughput that is defined in our system. That's the performance that we need to tweak. We commit one thing and we attain that one with our customer is what we are going to look for. But what you are asking eventually is going to happen when the load is higher, or even if it is, say for example, you guys ever heard of DDoS attack? It's busting every aspect into one system so that it would go down.
Yes.
Yeah, it's a similar way. If we start bursting with request, then eventually memory is going to die out, keep refresh, and then it kills the process that it's been using. That would happen in any system. That's why we are mentioning the throughput, bandwidth, and all those things. I think if we are lucky, I can show like, oh yeah.